Hi, this is Mike Richmond. It's time for another mini lesson in biostatistics. Today's mini lesson is specifically designed for students in Math 221B biostatistics. If you're taking another statistics class, the terminology used herein might or might not be the same as what you're using. Our discussion today is a little bit about populations and samples. So I want you to think about a population as being a set that is infinitely large. For example, if somebody says, my population is all 15 to 18-year-old boys in the United States, you might argue that that's not infinitely large. But some would argue that, well, the population includes all those people that are 15 to 18 years old currently living, and it might include all those people that maybe died before they hit the age of 15, and it might include all those people that were never born but might have possibly been born. Anyway, the purpose here is to help you to see that a population is something that's very, very large, and it can't be measured. It's infinitely large to the point that it cannot be measured. If you wanted to know the average weight of those 15 to 18-year-old boys, you couldn't do it because you just simply couldn't measure it. It would take too much time and too many resources, and you couldn't do it. There are lots of population parameters that exist. We're going to talk about several in particular for this class, and this is not a comprehensive list, but it's for the most part most of what we're going to use in this class. So I've listed some population parameters going from left to right, and in no particular order. I've got sigma, mu, p, and this funny little letter up here that looks like a P, but it's actually the Greek letter rho. So these population parameters are, sigma, for instance, is the population standard deviation. Mu is the population mean. P is the population proportion. And rho is the population correlation coefficient. And like I say, all four of these will be talked about in this class. Now, the thing about population parameters is we usually don't know what they are. They're unknown, and we can't measure them. In class, lots of times we act as though we do know them. We might take a historical value or something that we've looked at for a long, long time and consider that to be the population parameter. But that's just for academic purposes, and it's not really very accurately reflecting how nature behaves. Okay, so let's look at some samples. Samples are a subset of the population, and samples have these things that we can calculate called sample statistics. So, what's the main difference between population parameters and sample statistics? Well, population parameters are, like I say, they're unknown and I cannot calculate them, whereas sample statistics are numbers that I can squish around in my fingers, I can measure them, I can calculate means, differences, all kinds of different things there, and that's what makes a sample statistic different from a population parameter. You'll notice there's some alliteration going on there too, with the population parameters being P's and the sample statistics being S's. Anyway, bottom line is I can calculate sample statistics and I cannot calculate population parameters. I might, in a story problem, be told what the population mean is, but I can't calculate it. So if you're able to calculate something, you're actually calculating a sample statistic. Here's some of the common sample statistics we will be using, again in no particular order, throughout the course of the semester. First of all, there's n, which is the size of the sample. So if I take a sample of 36 adult women, my n would be 36. X bar is the sample mean. So I calculate the mean, I add up all the values, and I divide that by the number of values I've got. S is the sample standard deviation. The calculation of a standard deviation is a little bit more complex, so I won't go into that right now. You can easily find that in your textbook. But S stands for the sample standard deviation, and it's an estimate of sigma. In like fashion, X bar is an estimate of mu. So the sample standard deviation is an estimate of the population standard deviation, and the sample mean is an estimate of the population mean. Another sample statistic I've got is p hat. That's this p with this little angled thing on top of it. That's p hat. That implies that that's a sample proportion. So if I take a sample and I calculate the proportion of yeses in the sample, for instance, that would be the sample proportion, and that's an estimate of the population proportion, which is just p. Also, last but not least, when we get to linear regression, we'll talk about R, which is the correlation coefficient, and that is a sample correlation coefficient, and it's a good estimate of rho, the population correlation coefficient. I don't think the class we really talk about rho very much, other than just mentioning that it exists. Anyway, that's just a real brief synopsis of what's going on with populations and samples. Thanks for watching.